Yes, I'm going to take us back 50 or 55 years. I've been a ham now. This is incredible for 55 years. How many of you have been out there for that long? How many? Wow, look at that, okay? Because I'm going to be talking about the vacuum tube technology. Pardon me? You can't hear me. Hold on. Hello, test. Is that better? Hello, test. 1, 2. Very good. Okay. Still okay, or can you hear me okay? All right. I'm going to start this. I'm going to start this by telling you a story about before I was even an amateur radio operator. Hans, this is your fault, okay? Hans talked about vacuum tube safety. The vacuum tubes I'm going to be talking about here, the tubes themselves are safe, but they operate on higher voltages than the 12 volts that typically QRPers operate at, or even the 50 volts that some of the QRP or the QRO operators with solid state equipment operate at. And I'll tell you, my first experience with these voltages was when I was a Boy Scout and I was working for my radio merit badge, okay? And one of the things you had to do in the radio merit badge was you had to make a receiver. And at that time, transistors were extremely expensive. Back then, the equivalent cost of a transistor was about $50. And so a tube was $1 or $5 or something like that. So I tried to build this one tube receiver as part of my merit badge, and it operated on a 1.5 volt dry cell for the filament and a 45 volt B battery for the plate, okay? Now, the B battery was as wide and as thick as a regular 9 volt battery at that time. Everybody here is familiar with the 9 volt batteries, but it was about this tall, okay? Well, the radio didn't work. The receiver did not work initially. And I'm sitting here in grade school now. This is before I even went to high school. And I didn't know how to test anything. I didn't have a voltmeter. I had nothing. But I did know that you could test a 9 volt battery by sticking it on your tongue. And if you got a little bit of a tingle, that it was good. Well, being dumb and stupid, now I'm old and stupid, I took that 45 volt battery and I stuck it on my tongue. And then for 24 hours after that, this is what I talked like. And I had the biggest headache I have ever had in my life. And when my mother said what happened, I told her that I bit my tongue. Because I couldn't tell her that I was stupid enough to shove a battery into my mouth, okay? Now, I'm happy there were 90 volt batteries at that time, so thank God I didn't use a 90 volt battery, okay? I've since learned my lesson, okay? Yeah, I want to talk to you about vacuum tubes, and I'm not going to talk about the circuits that vacuum tubes use. You can get all you need about that in any, especially the older handbooks, are excellent sources, but many of the books, to me, as a physicist, get the whole thing wrong. They don't quite get everything the way it should be, okay? The proper way to look at the operation of these babies is to do it in terms of electric field, not positive and negative charges. That's really the wrong way to do it. Now, we could have a test here. Those 2 tubes that you see there on the screen, the one on the left, if any of you have Drake equipment, that's the 6JV6 that is so popular in the Drake line. And the tube on the right there is the 811A, which is very popular in some of the linear amplifiers out there. This is not for your QRPers out there. But of course, one of the reasons I'm talking about vacuum tubes is because there's a lot of interest in vintage gear. And all the really great vintage gear is vacuum tube. And I've actually run into people in Hamfests who say, you know, I'd really like to buy that rig. I mean, I'd love to get that, but they're afraid of trying to service it because they're afraid of vacuum tubes and they don't quite understand how they work. And that's what I'm going to show you today. I'm going to take you on an intimate tour right to the inside of a vacuum tube, okay? And you'll come away, hopefully, a little, did I just push the one button here? Let's see what happens. Oh, the arrows, okay. I'll probably go backwards, okay, forwards. There we go. To talk about a vacuum tube, you really have to talk about the original vacuum tube, and that's a light bulb. That is a typical incandescent light bulb, which just has a piece of tungsten in it. And I'm going to try and move this microphone again and maybe put it right below me here. And let's put it here. Let's put it so it points outside so that you can hear me no matter how I turn. Is that better now? Test 1, 1, 2, or? Okay, there, now I can talk. Okay, everybody has seen a light bulb. Well, maybe some really young people haven't seen an incandescent light bulb, but it has a piece of tungsten inside of it. The piece of tungsten is heated up with a current going through it, and it becomes white hot, yellow hot, in fact, okay? And it gives off a lot of light, and it gives off a lot of heat. What a lot of people don't realize is that provided it doesn't have any inert gas in it, most light bulbs have argon in them for certain reasons, but if it's a true vacuum bulb, what also happens is when you heat that baby up, the filament literally boils electrons out of it into the space around it. This is called thermionic emission. The temperature agitates the atoms and literally shakes the electrons out of the metal. And they fly out into the space around that filament. And one of the things the books never explain is how come they just don't fly off to the edges of the bulb and just dissipate? And that's because most of the books forget to tell you that when they fly out of the filament becomes positively charged. If you don't have enough electrons there, the filament becomes positively charged and it attracts the electrons back. And so what happens is they form a cloud around the filament. It's called a space charge. And it reaches equilibrium. So you've got electrons being boiled out, and then you've got electrons being attracted back in, and you have this continuous equilibrium. But you don't see that, okay? It doesn't really affect the operation of the bulb, okay? So we start there. It's not useful as far as electronics goes, but it sure does produce some great light, okay? Now, Thomas Edison built the first distribution systems for practical power, and he built them to run light bulbs, okay? So he was interested in the light bulb, and he was interested in making it work better, last longer, and so on and so forth. And so he began to study his light bulbs. One of the questions he had was, how come they turn black on the inside? The glass starts to turn black on these bulbs if they don't have that argon in there. And also, eventually, they burn out. What's going on there? Well, as part of his studies, what he did was he inserted, I think I went the wrong way, yeah. He inserted, come on here. Okay, one more. He inserted another element into the light bulb. We now call this the plate. I mean, when you're experimenting with stuff like this as a physicist, you just try everything you can. So he said, let me stick an electrode inside this glass bulb and seal it in there and fool around with it and see if I can figure anything out. And so you can see here in the diagram that there's this little rectangle behind the filament, and that's called the plate. And when he studied this, he found something remarkable. Now remember, this is in the late 1800s. This isn't in the night. This is before we even knew of the existence of the electron. They didn't know what electrons were. He put that baby in there, and lo and behold, what he found was that if he put a positive potential on that relative to if you put a positive potential there relative to that filament, by golly, electricity would flow through the vacuum of the tube with nothing in between. This is the first time anybody had observed current flowing through nothingness. Okay, that was amazing. Further, he found out that if he reversed the polarity and put a negative potential on the plate, no current flowed. It was a one-way valve for electric current. No one had ever observed this, at least in a vacuum, okay? The effect might have been observed in some solid-state things, but not in a vacuum, okay? Now, he thought this might be useful, so he concocted some sort of corny use for it, and he patented it. He patented everything he possibly could. That's what Edison was famous for, okay? So he really didn't know a use for it originally, but he eventually went and he patented this whole effect. And we now know, in terms of electron theory, what's going on. We know that electrons are being ejected from the filament because of the thermal agitation. This is called thermionic emission. Ion means charge, and emission means, or thermionic means because of heat. And they form this space cloud, okay? And that leaves a net positive charge, which keeps this cloud in equilibrium, okay? So how does a diode work, okay? How does that extra element work that he put in there? Well, now we can understand it. If we put a positive potential on that plate, what it's going to do is it's going to produce an electric field that's going to pull the electrons out of that cloud and pull them towards the plate and cause them to go to the plate. Now, as soon as they're pulled away and hit the plate, you got a current flowing around, right? You got that. But as soon as they leave the cathode, there's room for more of them there. And so ones come in from the cathode from the battery, they flow across, and you get a current flow all the way running around through the vacuum, through the battery, and around and around and around and around it goes, okay? If you put a negative charge on the plate, you produce an electric field. I'll be talking about this field, which pushes the electrons back into the cathode. They can't flow. And so there's absolutely zero electron flow in the reverse direction. Unlike a solid state diode, which has some reverse current, in a vacuum tube diode, the reverse current is essentially absolutely zero. Not even a picoampere of current flows. It's a true one-way valve, okay? Now, how do you make use of that? Well, one is once the alternating current power grid came into being, thank God Westinghouse won that little war between him and Edison, okay? There were still many cases where you needed direct current. If you had an electroplating operation and you wanted to plate copper plate things or silver plate things, you needed lots and lots of direct current. How are you going to get that from the AC grid? Well, you run it through one of these diodes and it cuts the current going the back way, and you've got direct current, okay? They are used in power supplies. Any device that needed direct current, you put this in a power supply. Industry would use them, and one place that they got used early on was in radio detection. In the very early years of radio, they did have sensitive detectors. They had coherers, they were called. They were electromechanical devices that were actually quite sensitive. They had galvanic electrodetectors and so forth in earlier radio. But these things that they had were persnickety. They weren't reliable. They were not always sensitive, and they were just difficult to use. You put a diode in there, one direction, that's highly non-linear. And you need, for a detector, you need a non-linear circuit. That's what you need. And so they started using them for radio detection. And they worked very, very well. But you had to pay whoever owned the patent on it. I don't know who got that radio patent, but you had to pay them for that. Patent rights back then were ferociously defended. They were ferociously defended, okay? So the diode was used early in radio for detection. So what do you want to do? Once you've got a device, what do? You improve it. You make a better mousetrap. You get a mousetrap, you make a better one. How do you make a better diode? Well, there's lots of ways to do it, okay? What I've got up here, how many of you have seen a 5U4? Yeah, okay, yeah. How many guitar players out there have a 5U4 in the back of their amplifier? Well, a lot of them, okay? One of the things you can do to make it work better is you want to improve the ability of the cathode to give off electrons. If you could do that, one thing you could do is lower the temperature of the cathode and save some of the wasted heat. But usually you just make the cathode smaller, coat it with special chemicals, typically rare earth oxides. You coat the thing, and then it can give off many, many, many more electrons. Okay, that's the first thing you do. Increase the emissivity, okay? Next, you put the filament inside the plate. In the earlier slide I had, you had the filament, and then out here, you had the plate. Instead, put the filament inside and surround it with the plate. That improves. The electrons can come out of the cathode in all directions instead of just one direction, so it works a whole lot better. Here in the 5U4, there are actually 2 units in the same envelope. So one thing you can do too is you can save space by putting two assemblies inside the same glass envelope. For full wave rectification, you need 2 diodes. So why not put them in the same bulb? And that's what they did. Here, you can see that the plate is actually a couple of pieces of U-shaped metal. It goes like this, up, over, and down, and then you put 2 of them back to back, and you have this rectangular shaped plate, and you shove the filament inside, okay? And this is how a 5U4 is typically made. There are 2 of them in there, and then you put it all inside of a glass bulb, and you suck the vacuum out, okay? The other thing you do, and I'll talk about this critically, is you decrease the spacing between the filament and the plate. This is going to be key in how these things work and amplify. When you make things more compact, you make it easier for the electrons to flow across because you increase the electric field. So you notice the glass bulb is pretty big. The actual assemblies are quite small. That can also lead to problems. You go too far, and what happens if you shake the tube or bump it? It short circuits. Then you blow out your capacitors that are supposed to be filtering the DC because they get AC. Okay, so there's always limits on what you can do in any of this, all right? Now, this is where we have to break away from what is said in so many of the books out there. Virtually all of the texts out there say that the plate attracts the electrons. Well, I hate to tell you, you can have a plate that's at 1,000 volts, and if you've got another plate next to it that's 1,000 volts and you put an electron between them, absolutely nothing happens. You have to have a potential difference, okay? The potential difference produces what we call an electric field. That is what applies a force onto an electron, okay? And what you do is you have a potential difference, and all electric fields come from a difference of electric potential or from a point charge. You arrange charges on the metal in such a way as to produce a potential difference and produce an electric field and therefore a force on the electron, okay? Do we have any electrical engineers out there? There's got to be. How many electrical engineers? Yeah, okay. I don't have to tell you if you went through electrical engineering school, calculating the electric field from an arrangement of charges is a big deal. Nowadays, we've got computer programs that can numerically do it just like that. But to do it and to program those things can take quite a bit. However, there is a case, one case, where finding out what the electric field is really, really easy. If you have 2 pieces of metal separated a distance d apart, it's really easy to calculate the electric field in between them, okay? It's very easy. All you do is take the voltage difference across those plates and divide it by the separation. Why is that important? Because it says the electric field and the force on the electron depends on 2 things: the voltage difference and also the separation between them. You can take a 1.5 volt battery connected to a couple of plates 1 millimeter apart, and you can get a huge electric field. You can get a big electric field by putting conductors very close together, even if the voltage is small. That's going to be key. And I think everybody should know that the direction of the force is always from the lower potential to the higher potential. You got something at 50 volts and something at 100 volts, it's going to be from the 50 to the 100 volt, not the other way. You got something at negative 50 volts and 0 volts, it's from the negative 50 to the 0. It's always from the lower to the higher, okay? This is exploited to a tremendous amount by decreasing the plate and cathode spacing in your diode. You increase the electric field because you make it smaller, and you make the electrons flow more strongly and faster and more efficiently. But you can only do it so far, okay? You do it as close as you can get it within manufacturing tolerances, okay? Go too far and it doesn't work. How else can you improve it, okay? Well, one way to do this is to use what's called an indirectly heated cathode. And in virtually all of the receiving tubes that you find in all of your amateur gear, except for the rectifiers, they've all got indirectly heated cathodes. The tubes in the power supply, the 5Y3, the 5U4, they have directly heated cathodes. But most of the tubes and all of that amateur gear out there and all that audio gear and stuff use indirectly heated cathodes. You take a tiny little tube, it's kind of hard to see there, there's a little tiny metal tube there, and you coat that tube with that rare earth compound. You'll see that in some of these close-ups I'm going to have. And then, this is, I don't know how they do this, but you take the heater and you coat it with ceramic because you're going to fold it back and forth and cram it inside that little tube. And not have it short circuit against itself, okay? That isn't easy. You can see little bits of the filament poking up right there out of that cathode, okay? And then when you turn on the heater heats the metal tube, and the metal tube and the coating emits the electrons, not the heater itself. And the result is you can greatly reduce the power needed to heat the tube. And also, because it's a piece of metal, the potential across the cathode is the same everywhere. And something like a 5U4, there's a voltage difference across the filament because it's got 5 volts across it. That can introduce hum. Okay, but by using, this is called a unipotential cathode, and it gets rid of that effect. This is a 12AX4, by the way. I'll talk about the numbering system of these babies in a little bit. Notice how the plate's made, by the way. Over here on the right, you may not be able to see it, but they take 2 pieces of metal that are shaped like this, like that. So they put a flat piece, a bend, and then another one, and they take 2 of them, and they essentially staple them together. Why do they have the extra part on the sides? That's because the plate gets hot when the electrons hit it. And there's no air in there to convect the heat away, so there's only one way to get rid of it, and that's to radiate it away. So the plate usually has got a flat area that is designed to radiate the heat through the vacuum out through the walls of the tube. Okay, that's all part of the people who design these things. Keep in mind that we're talking about a tube that's only about this big. These structures, folks, are tiny. They're little. That's why I say they're not low tech, or they're old tech, but they're not low tech. The mechanical complexities that they use to make these things blow me away. I look at these and I go, they made these things by the billions, okay? Not all the, I'd say not the billions, but by the millions, okay? Now, years ago, I went to MIT to an experimental physics seminar for a whole week. And one of the things I learned was, you can tell me, what does a bagpipe, a plumbing system, and a vacuum system all have in common? They all leak. They all eventually leak, no matter what you do. And the vacuum inside one of these devices has to be as good as or better than the vacuum of outer space. The vacuum inside that little glass tube is better than the vacuum in outer space. It has to be a really good vacuum. If any of those electrons hit oxygen or nitrogen, that's it. It's just not gonna make it. So how do you maintain a vacuum? they came up with a system that is so good that you can buy a tube that was made 50 years ago and it will still work. Now, not necessarily a transmitting tube, that's a different story. But the receiving tubes, as long as they're not busted, give them some time and the vacuum is still good. Here's what they do. They put a little ring inside the tube, little tray, and they fill that with a compound that has a voracious appetite for oxygen atoms in particular. It just sucks it up, okay? Now, of course, when you fill it, the outside surface of that starts absorbing it from the air. So they fill it and they immediately shove it in and evacuate the tube. Then, using inductive heating, they apply an RF field. This is the secondary of a transformer. It heats the tray and flashes the material onto the side of the tube. And there it sits, sucking up any extra oxygens or nitrogens that happen to encounter it, keeping the tube scavenged. Okay, this is called the getter because it gets the electrons out of the tube. Really, really technical name, right? The getter, okay? And one of the things that people don't understand is that produces this silvery look on the side of the tube. Some people think that means the tube is burned out. No, it's perfect. If it's gray, if that looks gray or whitish, it means that it's leaked and it's no good anymore. But that silver area means that it's got a good vacuum. This was great for me because my dad every so often would fix the TV, okay? He'd fix the TV. He'd take the back off and he'd test all the tubes and then pull out the ones that he thought were bad and buy new ones. And guess who got all the old ones? I did. He'd pull these ones out that were perfectly good. So I got a constant stream of tubes that were pretty good, okay? It worked out great for me, all right? All right, so remember when you see this, does that mean the tube is bad? It's probably just fine, okay? Now, the diode is great, but what happened was eventually several people, Armstrong, Fleming, and others, figured out that if you put another element inside the tube, shaped and positioned in the proper way, that you could control the current going from the cathode to the plate. And thus you could use the tube to amplify. And that structure we now call the grid. Now I have to tell you, I should have put a sense of scale in this drawing. This structure that you see here is smaller than my little finger. Okay, this is smaller than my little finger. I was talking to a friend back there, Jake, and he said, well, you know, what kind of a container do you put it in? I said, it's only this big. It's as big as my little finger. There are two of these inside of a 12AX7. Anybody out there who's got an electric guitar amp, anybody who's got a tube audio system, this tube's in it. Okay? Now you can see what I've been talking about. In this picture, you can see that the cathode is this tube down the center. You can't see the heater inside of it. You can see this whitish material on the cathode. That's the coating that gives off all the electrons. And then wrapped around it on these two posts is this elliptical grid of wire. Now, you have to look at the scale. Those grid wires are very, very tiny, and they are separated from the cathode by about the diameter of the grid wire itself. This is extremely close. That grid is very damn well near touching that cathode, okay? Almost touching that cathode. What that means is, if you apply a potential between the grid and the plate, which is behind it, I cut it all the way there, even a small voltage between that grid and between that plate is going to cause a large electric field to be developed, and that means it can have a substantial effect on the electron. You've got the plate out here, that's this gray background. That's positively charged or positive potential with respect to the cathode. So you want to take the electrons boiling out of that white area and yank them out. You produce an electric field from the plate that wants to pull them out and pull them to the plate. But you put a negative potential on the grid, usually. Not always, but usually you put a negative potential on that grid, and that produces an electric field pushing the electrons the other way. So by changing the potential that you put on the grid, you can decrease the current flowing in the device. Make the potential on the grid negative enough, you can actually stop, completely, totally cut off the flow of electrons in the device. So if you put a negative potential on that grid and then couple it through a capacitor to, say, an antenna, the tiny fluctuations in the antenna are going to cause tiny fluctuations in the grid voltage. That's going to cause tiny fluctuations in the plate current coming through, and it will amplify. And that is what we want to do with this thing, okay? The triode allows you to amplify what's going on. Think about this. This thing is the size of my little finger. They cram two of them into a glass envelope the size of my thumb, and they make these things by the millions. Through the 50s and 60s and even up into the 70s, every AM table radio had 5 of these things in it. They're making these things by the millions, okay? By the millions. It blows me away, the machines that could construct something like this. You could amplify with it, you could switch it, you could make it oscillate, okay? We've heard a lot about, what mode have we heard the most about today? Let's hear it, folks. CW. What the hell you mean continuous wave? It's being switched on and off. What do you mean continuous wave? Before the vacuum tube was the spark era. You turned a spark off and on with a key, and you interrupted a series of damped oscillations that were extremely wide bandwidth. As soon as they got the vacuum tube, they could make very small, pure oscillators that oscillated on one frequency. Now, they did have, in the spark era, does anybody know how they got continuous wave in the spark era around 100 kilohertz? They made alternators, just like the ones they used to generate the power grid, that could generate AC at 100 kilohertz. Think about that, how fast that thing had to go. Once they invented the vacuum tube, those things were gone. And you could make things smaller, and we were on the way to where we are now, where we got entire transceivers and a pack of cigarettes, okay? This opened up the entire field of electronics. You grab an electronics book before the transistor area, and the entire book from the rear to the index in the back is all about vacuum tubes and vacuum tube circuits. All of it, every single bit of it, okay? What's their problem? Well, they wear out, and they gobble up power, and they're big, okay? But boy, can they work, all right? Here's a popular one. I'm sure some people out there, maybe here at QRPville, we can't admit that we have a linear amplifier there. But those of you who do, it's probably, if it's an older one, it's got a 3500Z in it, okay? Very popular vacuum tube, a big one. That's why I've got it here. And if you look at one of these things, you can see that the plate is this pleated, it's actually a little cylinder. So the cylinder is maybe this big. It's about the size of your thumb. And it's got a pleated skirt around it to get rid of heat. That's why it's there. And then there is inside the filament up at the top there, up here at the top. And then the grid isn't a spiral of wire. It's like a miniature bird cage. It's a bird cage. It's a little bird cage that fits over that filament, and that's what you apply your RF drive to, okay? Here's a complete one here. One of these is capable of 750 watts PEP out. That's definitely not QRP, okay? So, but there are times, especially at the low part of the sunspot cycle, where you may have to use that, okay? But it's a wonder, it was specifically designed for hams. The 3500Z was designed so that a pair of them could provide maximum legal output. Here's my favorite, the 12AX7. They still make these, by the way. Still make them, still buy them. Go down to your local music store. You can buy one of these for maybe 15 bucks, which is not unreasonable given the technology that goes into it. This has 2 triodes in it. You saw the inside earlier. And they have a whole sequence of these from the 12AT7UX, blah, 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 blah. What you can do is you vary the spacing in those grid wires. You space those grid wires further out, it has less control and you get less gain. You put more and more grid wires in there, you get higher control and you get higher gain, always with a trade-off. If you put nothing but grid wires there, would it work? In other words, if you put a sheet of metal there instead of the wires, you wouldn't even get the electrons going through. So there's always a trade-off when you do this kind of stuff. And the people that designed these knew how to trade off, and they came up with a great product. Notice the halo here at the top. You know, that's you know, for us Catholics, that's what's over a saint, right? That's not to bless it. What is that? That's the getter. That's the getter. You look at the top of most 12AX7s, the top is silver because that's where they put the gettering material there, okay? It's fascinating. Here's another close-up of it. Look at the very tight tolerances that are involved here. It just blows me away. But they could make them, and there were times that you could buy them for $1 each. You could buy them for $1 each. And that back in the 60s, or $1.50 in the 60s, that's about what, 15 bucks today or something like that. That's still a very reasonable price. Now we have a problem. Okay, we got a problem here. Let's see which way I want to go. Let's go backwards. There we go. There's a big problem here, major problem. Okay, you've got 3 conductors. The plate, that's this gray area here that I've cut off in the front. You got the cathode in the middle. You got the grid sitting there. You got 3 pieces of metal separated by a perfect insulator. What are 2 pieces of metal separated by an insulator? A capacitor. You got a capacitor here. You got a capacitance, whether you want it or not. That's the thing. Whether you want it or not, it's there. There's a capacitance between the grid and the cathode. Dealing with that, I'm not going to go into it, but it has to be dealt with. But you've got an undesired capacitor between the plate and that grid. The plate's the output, the grid's the input. What happens if you got a capacitor from the output of an amplifying device to the input of the amplifying device and you feed it back in phase? What happens? It'll oscillate or it'll amplify more than it should. It becomes unstable. And in the early receivers, I'm talking about in the 1910s and 20s, this was a big problem in receivers. You would get this undesired feedback between the output and the input, and the darn thing would oscillate rather than amplify. And if you got 3 of these things stacked one after each other, and every one of them doing this, it was a nightmare, okay? They had to somehow get rid of this. And if this happens to be a power tube, instead of having, if you've got an AM station, and it's supposed to be a 1 kilowatt amplifier, and it becomes a 1 kilowatt oscillator, not necessarily on the frequency that you want it to oscillate on, what happens now? You've got all this energy being generated, won't go into the antenna because it's on the wrong frequency, so what happens to the circuit? It destroys itself. Okay? So what is done, even to this day, in triode amplifiers, is some of the output is intentionally fed back from the output to the input, but out of phase. And you adjust that so that it cancels the in-phase feedback. Anybody know what that process is called in an amplifier? Neutralization, okay? Neutralization. You better neutralize properly a triode amplifier, and some of you might have the amplifiers that they have very clever neutralization circuits, but they are there, okay? But you can't do this inside of a receiver. A receiver might have 3 triodes, and oh, this doesn't work. There's got to be a better way. How can you eliminate that? The answer is the tetrode. This revolutionized electronics. This is the schematic symbol you see here for the triode. There's a little loop there for the filament. This is indirectly heated cathode. There's the cathode. There's the grid, and there's the plate. And this is not to scale. You have to appreciate that if I drew it to scale, I'd have to almost take that grid line and I have it run right through the cathode. The separation is so small, you don't do that in the schematic, okay? The distance from the cathode to the plate is huge compared to the distance from the cathode to the grid. It just doesn't show up there. You add another grid very close to the control grid. And on this, you place a high positive potential. And it must be absolutely perfect. It has to be bypassed to ground so that there's no signal on that screen grid, nothing. It has to be absolutely filtered, nothing, okay? What that does is it shields the grid from the plate. Imagine if I just put a solid piece of metal between them. What would that do? Total the feedback, right? It also makes the tube so it doesn't work at all. So you start putting a few holes in that screen grid, or you make it into a grid of wire and you adjust the turns and so forth so that it shields the plate from the grid, okay? And this eliminates that capacitance and it stabilizes it, okay? This is called a screen grid tube, and it removed the need most of the time for neutralization, okay? And it revolutionized receiver design. Screen grid tubes came out in the 20s and early 30s, and they revolutionized the design of radio receiving and transmitting apparatus. That screen grid made a huge, huge difference, okay? But wait, it's not over. The screen grid in itself can cause problems. So let's take a look at this. Now, this is an extreme close-up of an EL34 audio amplifier pentode. I'm just going to ignore the extra grid out here. Just ignore it for the moment, okay? I'll come back to this, okay? The suppressor grid we'll talk about later, okay? What you see in this picture is in the middle, you see the white, which is the cathode. And the cathode isn't round, it's elliptical shaped. It's a squash tube. Nothing says it has to be round, okay? Then, very close to it, supported by this gold-colored wire there, very close in, are tiny little black wires that cross over the cathode. Those are the control grid. Notice how close they are. Again, they're almost touching the cathode. Then, supported by the black structure here, is the screen grid. All right? And that serves out in the background here, way, way back here outside, is the plate. Here's the plate. That screen grid serves as a shield between the control grid and the plate, cutting the capacitance and cutting the feedback. All right? Again, look at the complexity of this thing. Imagine the machines they had to make to be able to make these things. It just blows me away how they do this, okay? But here is the problem. All right, let's see. All right. The problem is this. Let me go back. Here's a common mistake I bet a lot of you make. You look at a schematic for your vintage transmitter, or your vintage, yeah, let's say your vintage transmitter, and it says there's 600 volts on the plate. Okay, the schematic says 600 volts. Is that the voltage on the plate? Is the plate always at 600 volts? No, if it was, there couldn't be any signal coming out of it. Under normal operation, the plate swings up typically to twice the voltage provided by the power supply and down almost all the way to 0 volts. It's swinging up and down and up and down. That means that there are times when the potential on the plate, which is out here, is lower than the potential on the screen grid. The screen grid is at a positive voltage. That's this black support here, and it never varies. And then out on the plate is going up and down. There are times when the plate is lower in voltage than the screen. Okay? Now that means if there happens to be an electron near the plate, pushing it away from the plate and back to the screen grid. Now that's not a problem normally. So the electrons come flying out, they come through everything, they're heading therefore to the plate, they feel a force against them, so it's kind of like a roller coaster going uphill, but they got more than enough energy to make it over the top. Fine, they slam into the plate, no problem. But there is a problem, okay? There is a problem. Let me ask this. Can you empty a bucket of water using a water hose? Take a fire hose, hook it up to a hydrant, and aim it into a cleaning bucket, and I guarantee you it'll empty the bucket. It'll empty the bucket. What happens is, when those electrons flying out that cathode strike the plate, they can cause electrons to be thrown out of the plate. And it doesn't take more than just a couple of volts difference for this to happen. As long as the plate voltage is about 20 volts or more, you get these electrons splashing out. It's like taking a water hose and aiming into a bucket and splashing some of the water out. If the hose has a strong enough flow of water, and you watch the amount of water in the bucket, it will slowly empty the bucket. It says, yes, but it'll empty the bucket. That's the point. And the bucket here is the plate, and we don't want to empty the electrons going to the plate. They're supposed to go out of the plate. This lowers the power output of the thing. You don't want those splashed out. What happens to those splashed out electrons is they get bumped out, and they find themselves, not all the time, but anytime the plate is lower in voltage than the screen, they flow to the screen. And you can actually, I've done this in the lab, I never believed it, but there is a way to set this baby up. You take a tetrode without this other grid, and what you find is as you increase the plate voltage, you know what happens to the plate current? It goes down. It goes down. I didn't believe that. It goes down. It goes up, and then it goes down, and then it goes back up again. That's called negative resistance, okay? You don't want that. Would you call a graph like this linear? No, I don't think so. Linear, okay. You don't want this effect occurring. So how do you get rid of it? Well, what they figured out was you put another grid here. See that silver grid right there? Now notice it doesn't have very many turns. It doesn't have very many turns. And it's much further out. It's much further out. They put another grid outside. Let's see if they put another grid outside here. And typically, that grid is grounded. So if you have a grounded grid here, and I mean it's DC grounded, it's got to be really well grounded. It can't have any, it's got to be truly grounded. That produces an electric field near the plate. The plate's always positive. The plate's always positive. The potential in the plate's swinging up and down with the signal, but it's always positive. And so there is an electric field in this case, which is always, after you pass this grid, towards the plate. So if you happen to be knocked out and splashed out of the pool, you are pushed back into the plate. It's like kind of like taking that bucket and putting walls on it that are really, really deep. So if you make the bucket deep enough, you can shoot the water in there and it won't come out. See? This is what they did. This is called the pentode. It doesn't take too many turns. Doesn't take too many turns, and it's very effective. Okay? And this then becomes the pentode. Right? This solves the secondary emission problem and cures it. And the example of tubes you might encounter in your classic amateur radio gear, okay, a 12BA6, okay, a 6AU6. If you had a 5-tube radio, an AM radio had a 12BA6, 6BZ6, EL3, these are all pentodes. Every single one of those is a pentode. It revolutionized it. The pentode is really the height of vacuum tube development. Think about a machine that can make all this and make these babies thousands at a time. It's just unbelievable. And make them economical. Now, the pentode was patented, which meant if you wanted to use it, you had to pay the patent holder. And so what people are always doing, many developments in electronics, we're trying to get around patent restrictions, okay? So the question is there a way to prevent the secondary emission, not have to have a suppressor grid? Can you do that? Then you don't have to pay the patent holder, okay? Okay? And that is the beam power tube. What you do here, okay, if you take a close look at this, now bear with me, you can see the cathode in the middle there coated. It's a rectangular shaped cathode. It's almost flat with the white stuff on it. And then on the left, you can see the 3 different grids there. Well, actually, you see 2 different grids. On the left, you can see a gold support and you can see a silver support. You can see the grids in the middle, but who can tell me what is special about those 2 grids? Can you see 2 grids? Can you see 2 grids? No. They are coplanar. They wind the screen grid so that the screen grid wire is right behind the control grid wire. So they don't just wind the grids, they wind them so that they're aligned with each other. So that when electrons come by the control grid, the screen grid is in the shadow of the control grid, which means few of them hit the screen grid, reducing the screen current. That saves energy too. But you'll notice in this tube on the right side, those support poles are supported by a shield which wraps around them. Here I have cut that shield and I have peeled it back so you can see the grid structure. And that shield is grounded. That shield is connected to ground. Any electrons coming off the cathode in the wrong direction have to go someplace. They're not going to go back to ground. So what do? They somehow make their way out through the gap between the 2 shields. So you have these 2 shields, and in between you just have the cathode and those aligned grids. They have to come out this way. You form them into a beam. Which this is called a beam power tube. Now, how does that work? Well, imagine you're in the plate and you just got knocked out. This is one of the things that 90% of electrical engineers forget. There are electrons flowing in space between the cathode and the plate. This is full of electrons flowing. That's how it works. If you are knocked out of the plate by secondary emission, imagine there's the plate, and you guys are all electrons coming in. I'm knocked out, and what do I see? All of these electrons flying towards me. Well, electrons are repelled from electrons. The space charge of electrons that are flowing out of the cathode repels those electrons that are knocked out of the plate and shoves them back without having to have that suppressor grid and avoiding the patent infringement. But it also makes it work one hell of a lot better. Anybody know what that might be there, that tube might be? Okay, let's talk about it. What was the first tube that did this? In 1936, General Electric used a marketing ploy to sell tubes. They put them in metal containers. All right? It's pure marketing fallacy. It was supposed to shield better. It's all a marketing trick. But among all of those tubes that they put out, many of which were the old glass tubes just stuck in a metal container, they put out the first beam power tube from RCA. It was developed by RCA, but GE. It was called the 6L6. Later in 1939 came a big tube, which is essentially a big 6L6, was the 813. And more followed until virtually every single television set in America in the 50s and the 60s, until transistors took over, had a beam power tube in it in the horizontal output stage. How many televisions were there in America? Oh man. And how many sweep tubes does that mean? Oh, every one of them had to have a sweep tube in it. Okay, they were all over the place. Okay, it revolutionized power and revolutionized design. Now, I've already showed you the schematic symbols. There's your diode and a triode. And when they classify the vacuum tube in this fashion, they don't count the heater. So a diode doesn't have a heater, a cathode, and a plate. They ignore the heater. The heater isn't counted when you categorize the tube. So a pentode has 5 active elements and then probably a heater, okay? As far as the envelopes, of course, glass, classic. Metal came in 1936. After World War II, most of the metal tubes came out in glass versions because the metal was expensive. They decided it really wasn't doing anything. There are ceramic metal tubes, your AA8V, 4CX250s, all these big power tubes. And there are some tubes, like the 6L6, that come both in glass and metal. You want to know one stupid thing about the metal? Can anybody tell me what's dumb about putting a metal case over a power tube? The heat can't get out. The heat gets stuck in the envelope, and the envelope gets hot from the heat. It's the dumbest thing I've ever seen. Typical marketing strategies, okay? The glass ones are far more powerful and can run much higher power because the energy can get out through the glass envelope, okay? Here's something I bet you a lot of you don't know. There is a numbering scheme, okay? The first number is the filament voltage. A 12AX7 has a filament voltage of 12 volt, actually 12.6, and a 6AU6 has or 6AL5 has a filament voltage of 6.3, and a 5Y3, 5 volts, and so on and so forth, okay? And there are 117 volt tubes too. There's a 117 volt power tube that you don't even need a transformer to run the filament. The middle numbers, the middle letters are just randomly assigned. Doesn't mean anything. But the last number is the number of total elements in the tube, in this case, in their infinite stupidity, including the filament, okay? So a 6AL5, which is 2 diodes inside of a common case, has got 1, 2, 3, 4, 5 elements. A 6AQ5, 1, 2, 3, has got, because the screen grid or the suppressor and the cathode are both cooked together, it's got 5 elements. The 12AX7, 1, 2, 3, 4, 5, 6, 7, and so on and so forth. Which means, if you look at a pentode, most of the pentodes end in 6. 6BZ6, 6AU6, 12B A6, and so on and so forth. Okay, there's actually some logic there. Okay, just about done. Testing tubes. Oh boy. There's only one true way to test a tube. Replace it with a known good tube. Honest to God, you laugh. For all of my tube equipment, I've got a backup set of tubes that I bought from a legitimate place, and you can't beat unplugging it and plugging the other one in. There are many tube testers out there. Most of them will tell you if it's burned out, if the filament blows out. They'll tell you if the elements short together, which can happen. And then they very crudely measure, are there any electrons coming off of the cathode, okay? And, but the good ones, which are very expensive, if you see one of these out there in the Hamfest, gobble it up. If you see a Hickok tube tester there, oh man, I've got one. These ones actually put a signal into the tube and see how much it's actually amplified and can actually tell you how the tube is doing. But for a transmitting tube, they cannot tell you how it is doing, okay? We're strictly for receiving tubes pretty much, okay? Hickoks are the best, but you have to always take them with a grain of salt, okay? Safety, okay? Number one, do not take a 45-volt B battery and shove it in your mouth, okay? That's the first thing. Second, I'm serious here now, the big ceramic tubes often use chemicals that are extremely hazardous. They're fine when they're the way they're supposed to be, but many of these big tubes contain barium oxide, which is an excellent insulator, yet it's a great thermal conductor. It is as carcinogenic as they come and as poisonous as they come. Unless you know what you're doing, don't go cutting apart transmitting tubes, okay? The smaller ones are made so that if you break them, obviously, they're not going to kill you because you busted a tube and dropped it on your kitchen floor, okay? But beware of cutting open certain of these tubes because they can be dangerous, all right? That's it. Questions? Any questions? Yes? Hold. Can you get to them? Sure. I'm the last one, right? So we don't have to rush out of here, so.
Okay, you ready? Early on when you were talking about diodes.
Diodes, yes.
Yes. I wanted to know how sharp of a knee do you get in a diode? How sharp can it be? In other words, how good is that diode?
When you mean in the plate current versus.
Well, you said it doesn't conduct in the reverse direction, but in the forward direction.
In the forward direction, okay.
Is the knee?
In any tube, because if you take any tube and you ground all of the other elements except the plate, it's a diode.
Right, I understand.
Okay. What happens is, as you increase the plate voltage, there's a very quick rise. There's a rise in the current that goes up, okay, and it's approximately linear, but it quickly, as you increase it, it will saturate. It will saturate. So if you take a tube and you keep increasing the plate voltage, there's a point where you suck every single electron off of that cathode and it saturates. The thing is this: most cathodes are so good that if you do that, the energy being deposited in the plate will burn up the plate.
Well, I was more interested in detection.
Oh, in detection?
Yes.
As soon as you have the smallest voltage in there, in the positive direction, it starts to conduct.
Did you ever observe to see how sharp it was?
I've looked at many texts, and yes, I have. It only takes a volt or two for it to come up to a significant value. So they're very sensitive. It also depends on whether you've got a transmitting tube that's a diode or a little tiny 6AL5 that's a diode. It depends on the structure of the tube.
I was thinking 6AL5 and then how sharp
6AL5
with respect to a germanium diode, for example.
Oh, it's much better than it. Okay. there's a good point. One of the differences between a vacuum diode and like a germanium diode or a silicon diode is that solid state diodes do not conduct in the forward direction until you hit a certain threshold voltage. It's about 0.3 of a volt for germanium and 0.7 of a volt for silicon. That doesn't exist for the vacuum tube diode.
That's what I wondered about.
That's the answer, yes. There's no threshold effect there. No.
Greg, a transoceanic, Zenith transoceanic radio.
Yeah,
Has
a
a
portable
1 volt.
one, a portable one, yeah.
Yeah, has that infamous 1 volt tube or
Yes.
1.5 volts, whatever it is.
Yes, yes.
Does that have like ultra tight clearances to get to operate on 1 volt, or is it a different coating, or what do you know
Okay,
about that?
first of all, the clearances depend on the plate voltage. What was the battery in that? There's a B battery in that thing. What was it? How many volts was it? 90 volts, okay? It is possible to get tubes that'll operate efficiently on 90 volts. In fact, the highest voltage in an All-American 5 radio, the highest voltage you can get is about 130 volts. So it is possible to have tubes that will operate effectively on lower potentials. Now, what they do in those tubes is the cathode is made, in fact, the cathode is not, they don't have indirectly heated cathodes. They simply have a wire in there that can get hot enough from that 1.5 volt battery. And so be warned, if you have a radio with like a 1S5 or 1R4 or a 3V4, if you look inside of them, you may not be able to see that the filament's lit. It's so dim, they try to draw as little power as possible from that battery that you may not be able to see that it's lit. That's one reason my 1S4 didn't look like it was lighting up, because I couldn't see it.
Is that a space charge tube?
No, no, no.
Is it a space charge tube, a very low voltage tube?
Okay, okay, let's talk about some other kinds of tubes. Okay. What other kind of, there are voltage regulator tubes. And a voltage regulator tube, like an OB2, an OC3, OD3, oh, there's a bunch of them. They're really cool to have in transmitters, because when you key it, they change their brightness and pulse with the keying, okay? There are tubes that have no filament, like an OB2. Actually, I'm wrong. It's not an OB2. Does anybody know what it is? It's a 0B tube. It's not an OC3, it's a 0C3. These have a gas in them, like neon or combinations of certain gases, so that when they glow, the property of a gas, when it's undergoing an avalanche, it's just like a Zener diode. So I think an OB2 is 108 volts. So if you put anywhere from about 3 to 30 milliamps through a 0B2, it'll measure 108 volts. An OA2 will measure about 150 volts. They're used for voltage regulation. And the circuits are absolutely identical with the diode. If you've got a transmitter with one of these, if you can get a powerful enough Zener diode, you could replace the tube with a Zener diode if you want. You could do that. So those are gas discharge tubes, okay? And we won't get into magnetic tubes like magnetrons and all that kind of stuff. Where do you find a magnetron? Microwave, yeah, okay. Yes.
This is the first time that I've ever understood, because of how clear and concise you were, the evolution of vacuum tubes and what caused them. My question for you is, starting with the simplest of them, the diode, and then ending where you did, what timeline are we talking about in history?
The beam power tube was developed about the end of the 1930s. By the end of the 1930s, these structures had been worked out. Like I say, the beam power tube came out in 36, okay? Now what happened is there was an evolution in the envelope and the ability to make smaller structures. Most of what you probably are familiar with are the glass miniature tubes, the 7-pin and the 9-pin tubes. The 7-pin tubes, I think, came in about 1941. So in 1941, the smaller tubes came in. The octal tube came in 1936. So when General Electric introduced all of those metal tubes, they also introduced the octal base.
Things got better at making it, so they got smaller.
I think so. Oh, the diodes came out in the early 1910s and so forth. You look at some of the first diodes that are really, really crude. Look up Fleming and look up Armstrong, look up the Fleming valve, and you'll see what these guys were doing. It's really amazing. Yeah. And one thing I will mention, one of the most, now I might be wrong here, I think it was the Armstrong patent. The structure of the grid and the spacing and all of that determines an inherent gain in the tube. That if you hook it up and you apply a plate voltage, you measure the plate current, and then you vary the grid voltage, you can generate what's called a characteristic curve. A curve that shows the plate current as a function of the negative grid voltage, okay? And that's a characteristic of the tube, okay? What they found in the early 20s and so far, it's early 20th century, was that they would hook up, Armstrong was one of them, they would hook up these tubes into a circuit, and the gain of the circuit was much more than it was supposed to be. Okay, it was much more. Even though there were, three people would construct the same circuit, and this one's getting twice the gain or 3 times the gain of that one. Anybody know what's going on? Regeneration. They finally figured out that the physical arrangement of the components would affect the gain of the tube. That some of the output was inadvertently getting fed back to the input, and that was raising the gain. And as I understand it, there was a huge patent fight over who truly discovered and should be credited with regeneration. Here is what is amazing, and I recommend it. You can look at QRP receivers. The simplest receiver that was used almost universally up until the mid-30s. In the mid-30s, the super heterodyne came in, and all the modern receivers are super heterodyne. Before that, it was the regenerative receiver. And you could take one of those 12 AX7s and put it into the proper circuit, and you could receive shortwave stations from all over the world. Go look at my web page, and you can see that there. You could increase the gain of the tube far, far, far beyond so that one tube could actually be a usable receiver. It wasn't selective, okay? And it wasn't very good on CW, but virtually all amateur receivers up until the 1930s, mid-1930s, every single one of them was a regenerative receiver. And then as soon as the super heterodyne was developed, it was such a step forward that we went completely to the super heterodyne. And also it was kind of bad too, because it meant that the complexity of the receiver design was pretty much beyond the ability of the typical ham. I want to put one little ad in here, okay? Tomorrow, can I call it show and tell? At show and tell, people come up, one of the most frequent questions I get is, what's your favorite rig? Well, my big rig is an FTDX 3000, okay? But that's not the rig I use most often. I have an 8-tube super heterodyne all-tube receiver that I use that I designed. I have a 2 or 3 tube transmitter that I use. And one of my other mantras is never abandon technologies. All technologies have something to offer. And so I use a digital VFO, okay? I start with a DDS VFO and a 2-transistor amp. That drives a 1-tube, 3-watt QRP transmitter, which you can come and see tomorrow. I'll have all this spread out. And that drives a 6146 amplifier. And then I also cheat with the receiver. The receiver that you can come and see is a 6-tube super het, and I'm proud of it. I'm going to brag. By itself, okay, it's stable as hell. It doesn't drift at all. And it's as sensitive as anything there is now, all the way up to 20 meters. If there's a signal there, it can pick it up. But it only has 2 kilohertz selectivity. It's got a crystal filter. So what do? I use a time wave audio filter, digital signal processing audio filter with it. And then I can get the selectivity down to 50 hertz, and that thing is stable enough to use that. And also, that time wave signal processor has automatic gain control. And when I add that modern audio digital filter to that receiver, it is as good as any current receiver. Now, it doesn't have a digital readout, and sure the hell doesn't have a wave, what do you call it, a waterfall display. But that thing, I've worked people, QRPs out there running 200 milliwatts, receive them just like that. I typically find that I can hear people that can't hear me wearing my 50 watts. They don't know how to operate their receivers. That thing is unbelievable. Tubes don't drift. It's the LC circuits they're hooked up to that drift. And if you go to my website and you look at my Wingfoot transmitter, which I did not design, it was designed by W80XI back in 1960, that radio has a tuned circuit that is separate. You go look in the handbooks, that the tuned circuit is separate from the main transmitter chassis. It's connected by cables to it. As long as the room temperature doesn't change on 80 meters now, that thing is as stable as any modern rig, and it's tube. Now, if the room temperature changes, well, that's different, okay? So there's always caveats here. And oh, by the way, on that receiver, you got to let it warm up for an hour. Everybody should know that. How many of you had a Hammerland receiver at some time? A few of you. If you were a rich one, what did it have in it? It had a Telechron clock. And that clock was there so that if you know you're coming home from work at 5 o'clock, you set that clock to turn on at 4, so that receiver was on for an hour when you got home. With tube equipment, it's normal for the VFO or any receivers to take half an hour to 45 or an hour to warm up. If you've got a piece of classic gear, give it 45 minutes to warm up. That's what it takes. That's what it takes. Other questions? I love questions.
Yes, there's one from Zoom.
Yes.
Shirley Dulce, KE1L. What about tubes with even more grids, like a pentagrid converter?
What about say it again, okay.
What about tubes with even more grids, like a
Okay.
pentagrid converter?
The pentagrid converter is a 12VE6, 6VE6, and so forth. The pentagrid converter is, there can be more grids than the 5 in a pentode. The pentagrid converter has additional grids. They're actually screen grids, so that a pentagrid converter is a frequency converter. It is designed to function as the oscillator and the mixer in a super heterodyne receiver. They are noisy as hell. They're great in AM radios, but you don't want to, the real way to do it is, I think I mentioned there are many purpose-built tubes. Like the 6BM8 was purpose-built for record players, okay? There's a whole class of tubes, and I'm going to throw some of these numbers out. Some of the older people will, like a 6EA8, a 6U8, 6G88. They are miniature tubes that have a triode and a pentode in the same case. The triode is for the local oscillator, and the pentode is the mixer, and they are specifically designed for frequency conversion, and they're much better than the pentagrid converters. And they cost a lot more. Like I say, I remember you could get at Olson Electronics for $1.99, you could get a 5-tube set for an AM radio. One of them was a power rectifier. One of them was the 35W4. Another was the 50C5, which was the beam power tube. Another one was a 12AV6, which is a triode and 2 diodes in it for detector and audio amp. Another was the 12BA6, which was the IF amplifier. And the other one was the 6BE6, was the converter. Who wants to take up what's a 6 plus a 12, or if you take a 12, you add up the filament voltages, guess what they add up to? 117. They put them in series so you could run all the filaments in series across the AC grid, okay? And that caused a big problem. What happens now? What about failure modes? Suppose you got one of these radios with these tubes in it, with these filaments that are connected directly to the AC grid, and the cathodes are typically grounded and they were connected to the chassis of the radio. And what would happen if there were a short between the filament and the cathode of one of those? Then the AC line would be connected directly to the chassis of the radio. And if you were like me and were a little kid that yanked the dial off the tuning thing and you touched the shaft, I'd get a hell of a lot more shock than that 45-volt battery, okay? Yeah, if you work on a classic 5 and service it, and these are really good things for restoration, you have to be aware that in some of those radios, one side of the AC line was connected directly to the chassis of the radio. In later ones, they coupled it and they floated the RF ground through a capacitor to avoid that. But if that capacitor should short, they could be dangerous. So if you work on any of those old AM radios, you should use an isolation transformer in order to keep them isolated from the supply. Okay. Well, the polarized plugs, that was the idea, right? A polarized plug would require you to insert the cord one way, right? Unless there was a little kid named Greg Latta who was replacing the outlets in the house and didn't know that it made a difference which way you hooked up the AC wires to the outlets. So I bet in my parents' house, half of the outlets are backwards and half of those polarized plugs connected the wrong way. So that's why that doesn't quite work, okay? Use an isolation transformer. Absolutely. Yeah. 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 What can happen? Or if you're lucky, you'll blow the circuit breaker. Oh yeah.
Who
Yeah.
makes the best tubes today?
Who makes the best tubes today? I can say who made the best tubes in the past. Muller did. I don't. You mean among receiving tubes? I don't think it makes a sense that you can get 12AX7s in any music store, and you can also get 6L6s at any music store. I really don't know, because the way people brand their products, for all you know, there's one manufacturer out there making all of them, and they stick different numbers on them. Okay. Generally, if you buy the regular tubes now, the small ones, they're new old stock. They've been around sitting on shelves for 30 years. So I guess it's sort of a non-answer, but it's hard to say. You know, iMac got out of the tube business. iMac doesn't make tubes anymore. They got out of that business. There's Chinese ones, and there's especially if you've got a 572B. I'm not going to even go there. For a while, the 570B transmitting tube, there was making them in China, and they were really shabby. I don't know if that's changed. Of course, that's because my amp hasn't, you know. So I can't really answer that. I'm not, yeah. Yeah, if you could. He's right back there. See, I can tell there's great interest in one of the nicest. Now, I'll tell you what my first transmitter was. Okay, I got licensed in '68 when I was 14, and I was delivering papers. And the only transmitter I could afford was 1995, and it was an Amico AC1. It had a 6V6 and a 6AX5 rectifier. And do you know how many papers you got to deliver to come up with 1995? And they charged you an extra $2 if you wanted to get the second coil for 40 meters. Okay? But it was a one-tube transmitter. It would run about 5 watts. And nowadays, if you go to my website, I've got all kinds of things there. I have on my website some information on coupling digital VFOs to some of these old tube rigs so you can drive them with enough signal. But with that 5 water, it was 5 watts out, 15 in. You know, you could work a lot of ton of stuff. It's a one, they key the crystal. And that's another point I'll mention. People will say that keyed oscillators have a bad note. It's not the tube, it's the crystal. Those old keyed oscillators were made to be used with FT243 crystals, which had a crystal that was about a 1/2 inch square or rectangular between 2 metal plates. And those metal plates could dissipate the heat from that crystal. You try and buy one of those tiny little crystals and hook it up to one of those old tube rigs, the thing will chirp like a bird because the current through the crystal is so high from the tube that the crystal heats up, changes dimension, and it swoops no matter what you do. So some people sell FT243 holders opened up with one of those little crystals shoved inside. They are not going to work the same. The best thing is to do what Hans did. In his, he had a separate oscillator, right, Hans, that he kept on all the time, and then he keyed the power amp, and that gets rid of the bad note, see. I would improve that, Hans, by putting a line in the crystal oscillator that shuts it off on receive via an extra relay on my antenna changeover relay. And that way it shuts it off and you don't have to shift the frequency. But it's wonderful, you know. Other questions? Yes.
While you're talking about tube technology, could you discuss remote cutoff tubes?
Yes. Yeah. Oh, thank you very much. Okay. A remote cutoff tube. The remote tube, one of the problems you have is if you have a receiver, everybody knows this, you want to have automatic gain control. Sometimes you don't. My receiver that you're going to see tomorrow at the show and tell does not have automatic gain control. That's contained in audio. But most of them, especially the AM radios, you got to have automatic volume control, right? Because you get distant and close stations, okay? What they do in a remote cutoff tube is they don't wind the grid uniformly. So what they have is the grid is wound far apart, and then it gets close together, and then it gets far apart, okay? And if you put negative voltage on the grid, it will start to pinch off the electron flow. Did I get it backwards? Maybe one way, what it does is it pinches the electron flow and forces the electrons to go through a place where the wires are further apart. I might have it backwards. The grid is not uniformly wound. It's open in some places and much closer in others, okay? And yeah, oh yeah, it starts like this, where you've got the grid, I think the grid is very closely wound, and then it gets like this, and then it gets close. So it has high gain with low voltages, and as you increase the voltage, you force the electrons to where the grid is further apart, and it has less gain. And you have electronic, not manual, volume control. And that they figured that one out back in the 30s too. Right away, they figured out how do you go to, they made a grid with non-uniform winding. Very good question.
Thank you, Greg.